friends, welcome to another lecture on convective heat transfer. So in today's lecture we'll be looking closely at the boundary layer flows in over a flat plate. We actually wrote the equations for that in the previous class, and we also looked at the analogy between momentum, heat and mass transfer by looking at the equations becoming exactly the same when they are normalized such that at the wall the variable is 0 and in the free stream the variable is 1, and when the Prandtl number and Schmidt number become unity, then the momentum equations, energy equation and the species equation become exactly the same equations with the same boundary conditions, and therefore their solutions become the same. So you can say that at unit Prandtl number and unit Schmidt number, the non-dimensional velocity gradient, non-dimensional temperature gradient and non-dimensional concentration gradient become identical. So there was a small correction about yesterday's class that I would like to take up first before we proceed with today's class. So let us look at the whiteboard. So in the last class we had said in Reynolds Analogy we said that when on the boundary layer the capital U, theta and Ci tilde, which are the non-dimensional variables that are being solved for, are defined such that they are 0 here and 1 here. U by U infinity, U is 0 here and U is U infinity here. Theta is T minus Ts divided by T infinity minus Ts. So at the surface T minus Ts is 0 and in the infinity it is T infinity minus Ts, so this becomes 1, and similarly Ci minus Cs divided by C infinity minus Cs for concentration. So all these values become 0 at the surface and 1 in the free stream. So when we wrote the equations also look identical provided the pressure gradient term is 0 and the pressure gradient term is 0 and the coefficient of the right hand side, which is 1 over Re for the momentum equation and 1 over Re PR or 1 over Re SC for the momentum, for the energy and species equations. When PR or SC or both are equal to 1, then the equation actually becomes exactly the same. So you have U del theta by del x plus V del theta by del y is equal to del y capital Y is equal to 1 over Re PR of del squared theta by del x squared plus del squared theta by del y squared. So we said that these equations become identical when I replace this with U or Ci tilde. All the other terms are identically the same provided this PR or SC become 1. So in the U equation there is only 1 by Re, in the Ci equation there is 1 over Re SC, and in the theta equation there is 1 over Re PR. So all these equations become identical with the same boundary conditions 0 here and 1 here if Prandtl number and Schmidt number are 1. So we said that that's called the Reynolds analogy, in which case the solutions are identical. So you get the gradients here, del U by del Y will be the same as del theta by del Y will be equal to del Ci by del Y at Y is equal to 0. That is, at the location of the plate all these gradients become identical. So when we did that, we actually said that del U by del Y, if I write del U by del Y is nothing but del u by del y, and there is a u infinity and LC. Okay, so u by u infinity and y by LC, that is this expression. Now if I write tau wall divided by rho u infinity squared, which is basically the non-dimensional form of this one. So if I write a half here and that's equal to Cf, then this tau wall is nothing but minus del u by del y into mu divided by rho u infinity squared with a half here. So if I rearrange this expression, I'll get minus mu del u by del y divided by rho u infinity squared is equal to Cf by 2. And if I write it in terms of the non-dimensional quantity, there will be a u infinity here and an LC here, and this becomes del u by del y. Then I get one u infinity getting cancelled, and this becomes an 1 over Re. So what I will get is, when del u by del y is required, this would actually become equal to, so if I write it on the next page, the tau wall by rho u infinity squared, which is Cf by 2, is actually equal to 1 over Re multiplied by del u by del y with a negative sign. Okay, so this is basically what I get. So if I say del u by del y is equal, I'll get the del u by del y is equal to, or minus del u by del y is equal to Cf by 2 into Re. And this is equal to, we said, del theta by del y, or del Ci by del y. Del theta by del y, if I look at the expression for Nusselt number, h into t infinity minus Ts is equal to k into del t by del y. Okay, so if I do it in the non-dimensional form with a minus so if I rewrite this, then I'll get h into LC by k is equal to del by del capital Y of t minus Ts by t infinity minus Ts. So I get a there is a minus sign that's missing somewhere. It's a minus sign here. Okay, so that is that. So this becomes equal to negative del theta by del y. Okay, and that is equal to the Nusselt number. So if del u by del y, minus del u by del y is written, this is also equal to minus del theta by del y, which is equal to Nusselt number. So in the same way, you can get the Sherwood number for the concentration term. So the term that we missed yesterday was this Reynolds number. Actually, the Nusselt number and Sherwood number would be equal to not Cf by 2, but Cf by 2 multiplied by the Reynolds number. So this is the correction that I wanted to convey yesterday. In the yesterday's class, we missed this Re, and that's something that you need to note. Okay. Now today we'll be looking at the solution of this boundary layer equation. We'll try to get what the solution looks like from the order of magnitude analysis on the governing equation. So you will get the form of the solution and not exactly what the solution is. So there will be some constants missing in the form of the solution. It will say the delta is such a function of x, or the Nusselt number would vary with Reynolds number in a particular way. The form of the equation would come, and the exact solution would actually give you the constants that are missing from that. But without going into detailed solution, just by orders of magnitude of the various terms, it also gives us a physical understanding of which term is more important, which term is less important, which is big, which is small, and at the same time it also gives you the functional form of the results that we are looking for. So that is the thing that we will do today. So let us start with the flat plate boundary layer. So suppose this is the plate, and the velocity of the oncoming flow is u infinity, and we said that there will be a imaginary layer inside which the velocity would vary from 0 to u infinity, after which the velocity remains nearly equal to u infinity. Okay. So this is your boundary layer. Suppose at any distance x, the thickness of the boundary layer is delta of x. If we look at the orders of magnitude of the various quantities in, for example, the continuity equation, you write the continuity equation in non-dimensional form: del u by del x plus del v by del y equal to 0. In this capital U is nothing but u by u infinity. So u, which is u by u infinity, varies from 0 to 1 in this region. So this is of the order of 1. So u is of the order of 1. Similarly, x is varying from 0 to LC, if LC is the length of the characteristic length of the plate. So x varies from 0 to LC. So x by LC is going to be of the order of 1 again. Similarly, y is going to vary from 0 to delta. Okay, so y by LC, the y is equal to y by LC, which is going to vary from 0 to delta by LC. Okay, so the y will be of the order of delta by LC. Okay, that is the range of that. So if I substitute all of those orders of magnitude here, I'll get a 1 by 1 here, and this, since this is equal to 0, I can say this is of the order of this term, which is b divided by delta by LC, which will basically tell me that v itself is of the order of delta by LC. Okay. Now this term of the order of basically is to say that it is not equal to that, but it is having a magnitude which is comparable to that. So that is the thing that we say. So in order to satisfy the continuity equation, if u and x are of the order of 1, then v will be required to be of the order of delta by LC, so that since y is of the order of delta by LC, you get that. Which basically means in boundary layer approximation we have said that this delta by LC is much less than 1, which basically means when u is of the order of 1, v is much less than 1 according to the boundary layer approximation. That's what your continuity equation tells you. Okay. So what does this mean? This basically means that the small v divided by u infinity is much less than 1, or small v is much less than u infinity, which basically means that in this boundary layer region, because the flow that is coming parallel is not able to continue in this region because the flow here is slower than the other, so there needs to be a small movement of the flow in the direction which is away from this plate, so that the mass conservation is correctly satisfied. So for that there is a small component of velocity in this direction, but that component of velocity v is going to be very, very small as compared to the velocity u infinity, which is the reference velocity for the x direction movement. So simply to say that the x direction component of the velocity u will be much larger than the y direction component of the velocity v. Okay. So that is the understanding that you get from this order of magnitude analysis, and that tells you that v is of the order of delta by LC, which we will be using in the momentum equation. The momentum equation basically says u del u by del x plus v del u by del y is equal to minus del p by del x plus 1 over Re multiplied by del squared u by del x squared plus del squared u by del y squared. This is the x momentum equation, and the y momentum equation says u del v by del x plus v del v by del y is equal to minus del p by del y plus 1 over Re times del squared v by del x squared plus del squared v by del y squared. So the first thing that we do in this is to take up this equation and look at the orders of magnitude. So you get 1 delta by LC by 1. Okay. So this is of the order of delta by LC, this is of the order of 1. So this is the first term, comma. The second term is delta by LC into delta by LC over delta by LC. So now this would get cancelled with this, so this term is of the order of delta by LC, this will get cancelled with this, so this is of the order of delta by LC, so this whole left hand side is of the order of delta by LC. Okay. Now this is going to be of the order of these terms. So I would say each of these terms on the right hand side is also going to be of the order of delta by LC. So del P by del Y is of the order of delta by LC, that is one thing that I get, and this term in which I can write this is 1 over RE, and this term will be delta by LC divided by 1 square, and here it will be delta comma, this is plus actually, delta by LC divided by delta by LC the whole square. Now the numerator being the same, denominator is 1 here and denominators are much less than 1 quantity here, so this term will be much larger than this term in the summation, and therefore in this equation this term will be negligibly small as compared to this term because of this order of magnitude. What does this say? This says that the gradients in the y direction are much sharper and therefore much larger in magnitude as compared to the gradients in the x direction, which we can understand. In the problem that we are looking at, which is the flow over the boundary layer, the accelerations, decelerations in the x direction are hardly anything. They are only small deviations because of the presence of the boundary layer, but other than that there is not much of an acceleration deceleration that happens in the x direction. But in the y direction, within a very small thickness, the velocity goes from 0 to u infinity. Therefore there is a much sharper gradient. So all the gradients in the y direction are much sharper than those in the x direction, so this term will get cancelled. In the same way, in this equation also this term would get cancelled, so you would only retain this term in the diffusion term. Now the next thing that we will look at is, okay, this is 1 over delta by LC, okay, and this is 1 over RE. So the whole thing on the left hand side is of the order of delta by LC. So you can say, if I cross multiply and take this side, then delta by LC the whole square is of the order of 1 over RE. Okay. What is RE in itself? RE itself is equal to rho u infinity LC divided by mu. Okay. So 1 over RE will have an 1 over LC in this case. So this is basically the order of magnitude. So the term delta, therefore, the delta is therefore going to be of the order of LC squared by RE square root of. So delta is of the order of LC by square root of RELC, and that if I can rewrite, let me clear this place and make space for the writing. So then this would be of the order of LC divided by the Reynolds number square root will be square root of rho u infinity LC divided by mu. So now these terms being constants, this is square root of mu. Okay, these terms being constants, if I can take them off, then this delta goes as square root of LC. Okay, so this is delta at LC, that is at the end of the boundary layer, but at any x, delta x is going to be of the order of square root of x, because that we can say whether we are looking at the boundary layer at this location x or this location x or this location, the boundary layer will keep changing, and the delta at any location LC is proportional to square root of LC, or of the order of square root of LC, multiplied by some constants that would appear here. So this is a thing that you would get, that delta at any location x is going to be varying as the square root of x. So as x increases, the delta increases as square root of x. That is the second result that we get. Okay. The other thing that you get is also that this del p by del y is also of the order of delta by LC, which is much less than 1, and this whole equation is of the order of delta by LC, which is much less than 1. So this whole equation is reasonably insignificant as compared to the other equation that we'll be just seeing. And the second thing that we get is this del p by del y is much less than 1, which basically means that the pressure gradient across the boundary layer, the pressure variation in y direction from the wall to the field, flow field, free stream, is negligible. Okay, it's a small quantity. So I can take the pressure inside the boundary layer to be the same as the pressure outside the boundary layer. Okay, so that is the assumption that we'll be making, which basically means that the pressure is not a function of y anymore, it will only be a function of x. So del p by del x will be equal to dp by dx in the other equation, and this p is only a function of x. Okay, so that is the thing that we'll get. And from this equation, using this kind of an approximation, only thing is this numerator will be all 1 here instead of delta by LC. You'll find that this is 1 over 1 square and this is 1 over delta by LC the whole square. So this term is much bigger than this term, so this term can be neglected. So if I do that and rewrite the first equation, I'll get a u del u by del x plus v del u by del y is equal to dp by dx with a minus sign plus 1 over Re times del squared u by del y squared. You are neglecting the del squared u by del x squared. Now in this, if I do the order of magnitude analysis, first thing that we will need to understand is that this pressure is the same inside the boundary layer as it is outside the boundary layer, and outside the boundary layer we know that it is a free stream, where there is no gradient of pressure. It's a uniform velocity flow. So it's a uniform velocity flow. The pressure gradient is only introduced by the plate, and that is negligible in the y direction. So the pressure in this case is uniform, and therefore px p is a constant, or dp by dx is 0. So this term which is written here is 0 for a flat plate. Okay, this is because there is no acceleration or deceleration happening in the free stream. Suppose I had a cone-like structure here, and the flow were coming here, and the flow were going up here. Because of this change in area, there would be an acceleration of flow, because of which there will be a non-zero dp by dx that is present. But since this is a flat plate, and there is no such wedge that is present in this particular case, it's only a flat plate. So the dp by dx, there is no acceleration and deceleration happening. This dp by dx is 0. So that is the thing that we have said here. If I do that, then this term disappears, and this is the equation that I get. Okay, and in this equation, if I again do the order of magnitude analysis, I know the order of magnitude of delta also, which I can use later. But basically I'll get 1 over 1 comma delta by LC 1 over delta by LC, that is the two terms that is on the left hand side. So both of these, now this cancels out with this, so both of these are of the order of 1. Okay, and this is of the order of 1 over Re multiplied by 1 over delta by LC the whole square. Okay, now this would basically again tell me that now 1 over Re delta by LC the whole square is of the order of 1. So delta by LC the whole square is of the order of 1 over Re, which is the same result as we got in the previous page. Delta by LC is the same of order of 1 over Re. This is the expression that you had. So we'll basically be able to write the same thing, that delta squared is of the order of LC squared by Re LC, or delta is of the order of square root of LC. This is the same result as you got in the previous page. Okay. So what comes out from this order of magnitude analysis is that the boundary layer thickness goes as the square root of the length, and the boundary layer thickness at any x goes as square root of x. This is something that we get. And the second thing that we get from this analysis is that the the second term that we write in the governing equation, the second term that we write in the governing equation, del squared u by del y squared on the right hand side, is much bigger compared to the first term in the diffusion term, and therefore the second gradient with respect to x is neglected with reference to the second gradient term in y. So that brings us to the boundary layer equations as del u by del x plus del v by del y equal to 0, u del u by del x plus v del u by del y equals 1 over Re into del squared u by del y squared. These are the two equations that one needs to solve with the boundary conditions that at the wall u is 0 and in the free stream as y tends to infinity u tends to 1. So this is the condition that you would have, and you will solve this equation mathematically or analytically. But if you solve that, what will you get? You will get the del u by del y at the surface, which is basically what we are looking at as solution here. So the tau wall divided by half rho u infinity squared, which we wrote in the previous slides as CF, and this we wrote it as del u by del y with the negative sign, right, multiplied by Re. This is the expression that we wrote. Actually, we wrote it for CF by 2. Okay, this is the expression that we wrote. So if we want to get this non-dimensional gradient in terms of del u by del y, this del u by del y is going to be of the order of 1 over delta by LC or delta by x. So at any given x, this is going to be of the order of 1 over delta by x, and therefore CFx by 2 is going to be of the order of when it is of the order, you can forget this by 2. The CFX or CFX by 2, okay, let it be there, is going to be of the order of 1 over delta by x into Rex. Okay, and this 1 over delta by x we said is going to be of the order of square root of Rex right. So then delta itself is going to be of the order of square root of Re, but delta by LC is of the order of 1 over square root of Re. Okay, so this is basically what we will use in this expression. So sorry, I had put the Re in the wrong place. So this multiplied by Re is del u by del y. It's what we actually got. Okay, so CF by 2 into Re is the minus del u by del y term that you got. So CF by 2 into Re is this, which is of the order of square root of Rex. This is what we have found. So then CFX by 2 is of the order of 1 over square root of Re. Is basically what you get. So there are two results that we have got now. One is that delta by x is of the order of 1 over square root of Rex. Okay, so this is one result that we have from here. Okay, delta by x is of the order of 1 over square root of Rex, and here we have got CFX by 2 is also proportional to 1 over square root of Rex. So we basically say that this del u by or if you want to write this CF by 2 into Re, then that will be proportional to square root of Rex. Okay, so this is the result that you get. CF is 1 over square root of Rex and CF into Re is square root of Rex. So this is the result that you have. So this gives you the solution for the fluid mechanics part of it. What is the non-dimensional shear stress at the wall? Non-dimensional shear stress at the wall, which is tau wall divided by rho u infinity square. Let's go back to that slide where we derived at the beginning. Yes, so tau wall by rho u infinity square, which is Cf by 2, is given by 1 over Re into del u by del y, and this del u by del y itself is in this particular case, so it is 1 over Re multiplied by this will be 1 over delta by Lc, okay, and 1 over delta by Lc is nothing but Re itself. So this will be you will get a square root of Re divided by Re. So this is of the order of 1 over square root of Re. Okay, so the shear stress Cf by 2 is going to be proportional to 1 over square root of Re, and that's the result that we finally have ended up with in this derivation. Okay, so Cfx is going to be proportional to or of the order of 1 over square root of Rex. It will be some constant times that, and delta by x, that is the boundary layer thickness at any x as divided by x, will be 1 over square root of Rex. So these are the two non-dimensional results that we have. If I solve these equations completely analytically, then I will be able to write what is this equal to. Okay, so if I solve these equations, then basically I get delta by x is equal to 4.92 divided by square root of Rex. Okay, so this is one result that I get by completely solving this equation. Similarly, from this I get Cf by 2 is equal to 0.332 divided by square root of Rex. This is the second result that I would get if I solve this analytically. Analytical solution will basically give me okay, the analytical solution will basically give me a velocity profile. I'll say wherever the velocity profile is such that capital U is 0.99, what is the value of y, and that is the value of delta that I'll define, and that delta at any x can be found out to be this. Okay, and using that value of delta, if I calculate the velocity gradient at the y is equal to 0 location, then it will give me the shear stress, and therefore the value of the skin friction coefficient Cf according to this expression. Cf by 2 is equal to 0.332 divided by square root of Rex. So this is the fluid mechanics solution, and once you have the fluid mechanics solution, in order to get the heat transfer solution, there are multiple possibilities. One possibility is that Prandtl number is equal to Schmidt number equal to 1, which is the Reynolds analogy. Okay, so this is valid when the mechanism of momentum transfer, heat transfer and mass transfer are the same, and this happens in gases. So in gases, what is the situation? Suppose I have two layers of fluid adjacent to each other, and this is flowing with some velocity and this is flowing with some other velocity. Because of random motion of molecules, some some molecule from here would move from this layer into this layer, but it has the momentum carrying the velocity of this layer, and therefore it drags this layer of fluid further up because of the higher momentum that it has. Similarly, another particle which is in this layer, which has a lower velocity, moves into this layer and it tries to drag the upper layer back, and that is the mechanism of viscosity. Okay, in the same fashion, if this is at some temperature T1 and this is at some temperature T2, the molecules that move from here to here would take the effect of T1 into this layer, or the ones that move from here to here would take the effect of T2 from there to there, and therefore there is a mechanism of conduction that is established. In the same way, the concentration. So in gases, it's the same random motion of molecules from one layer to the other that causes the mechanism of momentum transfer, heat transfer, as well as mass transfer. So they are analogous and similar mechanisms, and therefore the Prandtl and Schmidt numbers for gases typically is observed to be of the order of 1. So for air, for example, at let us say 20 degrees Celsius and 1 atmosphere pressure, we find that the Prandtl number is about 0.71. And even when you increase the temperature of air from room temperature all the way up to 500, 600, 800 degrees Celsius, the Prandtl number does not change too much. The viscosity changes, the conductivity changes, but the ratio, the mu Cp by K, which is a Prandtl number, that remains more or less unaltered with minor variations from 0 degrees Celsius to even, for example, 1000 degrees Celsius. So that is the Prandtl number equal to 1 for air. Similarly, Schmidt number is also of the similar order for air. So Reynolds analogy is therefore directly applicable to gases. We can use Reynolds analogy. And if I use Reynolds analogy, what does it tell me? It tells me the Nusselt number, which is del theta by del y, with a minus sign, of course. This is the Nusselt number. This is equal to Cf by 2 into Re. Okay, so what is Cf by 2 to Re? This is basically 0.332, okay, multiplied by square root of Re. Okay, so this is basically what you get. Why do you get that? Because we have said that Cf by 2 is 0.332 divided by square root of Rex. So if I multiply by Re, there will be a root of Re on the numerator, and that's what you get here. And this would also be equal to the Sherwood number when the Reynolds analogy is valid. Okay, so we only need to solve for the fluid flow and get the result, and using the same result we can actually write the Nusselt number as well as the Sherwood number. But what is this Nusselt number? This is H at any x. Okay, so this is Cf at the same x, this is nu x, which is the H at any x, multiplied by x divided by Kf, and this is given by 0.332 into Re to the power of half. Okay, and what is this Re itself? The Re itself is rho u infinity x divided by mu. Therefore, there is a square root of x on this side and there is a x on this side. So if I rewrite the expression for H, it will have a different dependence on x as compared to the Nusselt number. Let us look at that. The Nusselt number at any x is going to be equal to 0.332 multiplied by rho u infinity x divided by mu, whole thing raised to the power of half. Okay, but what happens to the Hx, which is so I'll write this Hx into x by Kf is equal to the same quantity, and therefore Hx will be actually equal to this x will go and divide there, so x will be come below. So you'll have a 0.332 into rho u infinity by mu to the power of half. Okay, and then you get a Kf multiplying here, multiplied by x to the power of, there is a x to the power of half here, and this x goes and divides there, so there is a x to the power of minus half. Okay, so if Nusselt number increases with x in the way of x to the power of half, the heat transfer coefficient decreases with x as x to the power of minus half. That is the dependence that you will need to understand. Now this is the x H at any x. Suppose I have a plate with different values of H at x as given by this expression. Then if I want to get the overall heat transfer coefficient, then if I define the q dot is equal to integral of H into A into delta T, and this is what is the area? The area is, if I take an infinitesimal distance dx here with a unit depth perpendicular to the plane of the board, then this A is 1 into dx. Okay, and if I integrate that, this is H at x from x is equal to 0 to LC, if then LC is the length of the plate, then this is overall q dot. This is the total heat transfer from the plate. If I then write this as equal to an average heat transfer over LC into A into so this is dA rather, A into delta T, where delta T is the same, it's T infinity minus Ts. Okay, so here also it is T infinity minus Ts. It's the same. So this area is nothing but now LC into 1. Okay, so if I define then H bar at LC, this will actually be equal to H bar at LC, that is the average heat transfer coefficient over the length, will be equal to integral 1 over LC. Okay, so this LC is going there, delta T will get cancelled, 1 over LC, integral from x is equal to 0 to LC Hx dx is what you will get. Okay, so this is the definition of the average heat transfer coefficient, and the average Nusselt number will be defined on the basis of this. So Nu bar at LC will be H bar LC into LC divided by Kf. That is the definition. So when you want to find the average Nusselt number, it is not the Nusselt number that is integrated over the plate. You actually write the heat transfer coefficient over the plate, integrate the heat transfer and get the average heat transfer coefficient, and then define the NuLC. So the integral is of x to the power of minus half dx rather than x to the power of half dx. Just be very careful about that. The integral is always of the heat flux, which is H delta dA into delta T, and not the Nusselt number. Okay. So, and you see that the Nusselt number has an x to the power of half variation, and the heat transfer coefficient has an x to the power of minus half variation, and that is because there is an x in the definition of the Nusselt number. This is something that you will need to be extremely careful about. Okay. So whenever we need to define an average heat transfer coefficient over a surface, we always integrate H and not Nusselt number. Okay. So we'll remember that when we go further. So what do we get here then? Nu bar for any plate will actually be integral of H dA, and since the H has the x to the power of half condition, the integral will have a factor of 2, so you will get 0.664 into ReLC to the power of half is what you will get for the value of Prandtl number and Schmidt number equal to 1. Okay. So for Reynolds Analogy case, we said that the Nusselt number is 0.332 square root of Rex, NUX is square root 3.332 square root of Rex, which is also equal to Hx. The Nu bar, which is the average heat transfer, average Nusselt number over the plate over LC, will be 0.664 square root of LC, and similarly the Sherwood number average will also be 0.664 ReLC to the power of half. So this is all valid when Prandtl number equal to Schmidt number equal to 1 in Reynolds Analogy, because we have got this result directly from the CF by 2 answer. Okay. What happens when Prandtl number or Schmidt number are not equal to 1? Okay. Now this is something that we'll need to closely think about to understand. What is Prandtl number? Prandtl number is nu by alpha, which is the momentum diffusivity divided by the thermal diffusivity, and this is nu by d, the momentum diffusivity divided by the mass diffusivity. So what do you mean by Prandtl number not equal to 1? It basically means that alpha, which is the thermal diffusivity, is not the same as nu, but it can be different. So if I choose a different fluid instead of gases, if I choose a liquid for example, then the alpha can be very different. The nu will increase when I choose a liquid, the nu will be higher for liquids than for gases, and so the alpha value will determine what will be the Prandtl number. So if I have a liquid with high conductivity, which is high K, and you have a liquid with low conductivity. Let us give examples. High conductivity can be liquid metals. Say for example mercury is a liquid metal that we know at room temperature, but at elevated temperatures you can have other metals also which are in the liquid form. Say for example, molten steel in the steel plant is a liquid metal. Such substances which have a high value of K and therefore a high value of alpha will have a Prandtl number much less than 1. Okay, because alpha would be much greater than nu and therefore Prandtl number will be much less than 1. So this is the case of liquid metals. Okay, and what happens for low conductivity materials, like for example oils which have a high viscosity but poor conductivity, they'll have a Prandtl number which will be much greater than 1 because nu is much greater than alpha. What happens when these things happen? So in the case of Prandtl number equal to Schmidt number equal to 1, the thickness of the boundary layer that we were looking at in this, this thickness delta for velocity to reach from 0 to u infinity, and the value delta T, which is the thermal boundary layer thickness, for the temperature to reach from Ts to T infinity, or for that matter delta C, the thickness that is required for the concentration to go from Cs to C infinity. Okay. In the case of Prandtl number and Schmidt number being equal to 1, the diffusivities of all three are equal, and therefore delta, delta T and delta C are all identical. So there is a single thickness of the boundary layer. There is no difference between boundary layer boundary layer thickness delta for velocity, delta T for temperature, or delta C for concentration. But in the case of non-unit Prandtl number, that is when I have Prandtl number much less than 1, okay, in liquid metals, what happens? The diffusivity alpha of heat is much higher than that of nu, and therefore the thermal boundary layer will be much thicker because the heat is able to penetrate much further as compared to momentum into the medium, and therefore the delta T will be much greater than delta when Prandtl number is much less than 1. Similarly, in this case, momentum is able to penetrate much deeper, and therefore delta is much greater than delta T. Okay. So what happens under these conditions in the boundary layer is what we would be looking at now. So let us look at the low Prandtl number case first. So there is a plate, it's a flat plate. Okay, there's a plate, and let us say this is the thick thermal boundary layer and this is the thin momentum boundary layer. So this is delta and this is delta T. So delta T is much thicker than delta. So what happens? The velocity reaches u infinity right here and remains u infinity throughout the thermal boundary layer. So the velocity is u infinity. Since this thickness is negligible compared to this, we can say that the entire thermal boundary layer has u equal to u infinity, and therefore u by u infinity is equal to 1 in the case when Prandtl number is much less than 1 throughout the thermal boundary layer. Okay, so u is equal to 1. Okay, and the other quantities, when I write the continuity equation del u by del x plus del v by del y equal to 0, this u is of the order of 1, that is fine. This x is of the order of 1, of course, because the length is LC, which is not changing from the previous discussion. Y is now going to be of the order of delta T by LC, because we are looking at the thermal boundary layer thickness is where we are doing, and therefore the order of magnitude will tell me V is of the order of delta T by LC. Okay, so that is your first thing. So V is of the order of delta T by LC, U is of the order of 1, and Y is of the order of delta T by LC. When I write the energy equation, U del theta by del x plus V del theta by del y is equal to 1 over REPR multiplied by del squared theta by del y squared. This is my energy equation. Now in this, theta is of course of the order of 1 because it changes from 0 here to 1 here in the thermal boundary layer. So theta is of the order of 1, x is of the order of 1. This is delta t by LC, and this is delta t by LC. So what I'll get is 1 over 1 and delta t by LC and 1 over delta t by LC. So that gives me the whole left hand side is of the order of 1. Okay, and this is of the order of the right hand side, which is 1 over REPR multiplied by, this is 1 over delta t by LC the whole square, which tells me delta t by LC is of the order of 1 over REPR, or delta t is this whole thing to the power of half. Okay, because it's delta t by LC the whole square is of the order of 1 over REPR. So delta t by LC is of the order of 1 over REPR to the power of half. So what happened? We have a very similar result as in the case of the velocity case, except that there is a Prandtl number here. So what do we get? We have delta is of the order of 1 over, or delta by LC is of the order of 1 over RE to the power of half, and delta t by LC is of the order of 1 over REPR whole to the power of half. This is the difference that you get. And when I write Nusselt number, which is del theta by del y at y equal to 0 with the negative sign, of course, this actually becomes in the order of magnitude is of the order of 1 over delta t by LC. Okay, and 1 over delta t by LC is of course REPR to the power of half. So Nu is of the order of REPR raised to the power of half is the result that you get for the case of low Prandtl number, that is Prandtl number much less than 1. Okay, and similarly, when I look at the case of large Prandtl number, then what happens? This is for liquid metals, that is Prandtl number much less than 1. Okay, when Prandtl number is much greater than 1, what happens? Delta is much greater than delta t, so you have a small delta t here and a very thick delta. Okay, and now you are solving the energy equation only inside this thermal boundary layer, which is delta t, and inside that, if I look at the velocity profile goes to u infinity here because its delta is so thick. So the u value that is reached here is much smaller than the u infinity. Okay, so u is not going to be of the order of 1 anymore, capital U, but it will be of a smaller order. How do we estimate that order? It's only order of magnitude. So instead of a curve, if I consider this to be a straight line where this is delta t thickness and this is delta thickness, and there is a linear variation there, then I will be able to say u goes from 0 to u infinity at capital delta. So the u at inside this boundary layer is of the order of u infinity by small delta into delta t. That is the order of u, and therefore from this I can write u by u infinity, which is capital U, is of the order of delta t by delta. Can I write that? Okay, so this is one thing. And if I substitute this into the continuity equation, del u by del x plus del v by del y equal to 0, where y is of the order of delta t by LC, okay, then this x is of the order of 1, and u, of course, we have said is delta t by delta by 1, comma, this is of the same order of v by this is delta t by LC. So you get v is of the order of delta t square divided by LC delta, right? So that is the order of magnitude that I get from the continuity equation. If I substitute that into the energy equation, u del theta by del x plus v del theta by del y is equal to 1 over REPR multiplied by del squared theta by del y square. Okay, so in this, if I put the orders of magnitude, Okay, let me write that here. The left hand side you have 1 and sorry, this is not 1, it's delta t by delta, that is u, multiplied by 1 over 1, and the second term is delta t squared divided by delta LC, and this is 1 over delta t by LC. These are the two terms on the left hand side. Now the delta t by LC cancels out here and you get a delta t by delta, so the entire left hand side is of the order of delta t by delta. Is that right? And on the right hand side you have 1 over REPR multiplied by, this is 1 over delta t by LC the whole squared, and this is of the order of delta t by delta, right? That's the left hand side. So if I put all these things together there, I'll get delta t cube divided by LC squared into delta, okay, is of the order of 1 over REPR. Now let me do some readjustment here. This delta, I will take it as delta by LC to the other side. So what I will do is I'll make this into LC cube and a delta by LC on this side. Can I do that? And when I write delta by LC on this side, from the fluid mechanics solution, I know this delta by LC is of the order of 1 over RE. Okay, so 1 over square root of RE. So this then is of the order of RE to the power of minus half okay, let me just write this 1 over REPR and 1 over RE to the power of half. So what do you get there? This is therefore delta t by LC the whole cube is of the order of 1 over RE to the power of 3 by 2 PR to the power of half. No, not PR to the power of half, it's PR. Right? RE to the power of 3 by 2 PR. So if I take the cube root of both sides, I'll get the order of magnitude delta t by LC. So that tells me delta t by LC is of the order of 1 over RE to the power of half PR to the power of 1 by 3. Okay, so this is the result that I have, quite interesting. This is for Prandtl number much greater than 1. What do we recall from Prandtl number much less than 1? Delta t by LC is of the order of 1 over RE to the power of half PR to the power of half for Prandtl number much less than 1, and delta t by LC is equal to, or is of the order of 1 over RE to the power of half for Prandtl number of the order of 1. So in all these three, the RE to the power half is common. Okay, and because Prandtl number is 1 here, the power of Prandtl number actually doesn't matter here, so it could either join here or join here. Okay, and for large Prandtl numbers, the dependence is on Prandtl to the power 1 by 3, and for small Prandtl numbers, the Prandtl power half is the dependence. Okay, so this is what you get, and accordingly the Nusselt number will just have the inverse dependence. So the Nusselt number will be proportional to RE to the power of half PR to the power 1 by 3 for Prandtl number much greater than 1, REPR to the power of half for Prandtl number much less than 1, and RE to the power of half for Prandtl number of the order of 1, and that's exactly what we get. So we'll write down that Nu at any x is equal to for Prandtl number much less than 1, and for Prandtl number much less than 1, you get REPR per half, so you get 0.564 into REPR whole thing raised to half for Prandtl number less than around 0.5. Okay, so for small Prandtl numbers starting from 0.5 downwards, it is this, and equal to 0.332. This is a number that you might probably be more familiar. Re to the power of half Prandtl to the power of 1 by 3 for Prandtl number greater than about 0.5. So this is the result that you get. This is for NUX, and therefore NU bar when you integrate it. So the Prandtl number of the order of 1 joins this one. When Prandtl number equal to 1, it is 0.332 Re to the power of half, which is the same as the result that you had got earlier. So the Prandtl number greater than 1 and equal to 1 combine into the same club, and Prandtl number less than 1 goes to a different club here. Then that's the thing that you get. Okay, and NU bar L. So you remember that this is NUX, which is h into x by k. So when I divide by x, this Re has x to the power of half, so it becomes x to the power of minus half. So here again it becomes the same thing. So when x to the power of minus half is integrated, there is a factor of 2 that gets added to both. So both of these actually just get doubled for the length LC. So this will become 1.128 into this is Rex, right, and this will be ReLC into PR. Re, this whole thing to the power of half for Prandtl number less than 0.5, and it will be double of this, 0.664 into Rex to the power of half and Prandtl to the power of 1 by 3 for Prandtl number greater than about 0.5. So this is the result for laminar boundary layers that we will get. Okay, we'll talk about transition and turbulent boundary layers in the next class before we move on to the other discussions on averaged Nusselt number and local Nusselt number relationships and deriving average Nusselt number for turbulent boundary layers. So at the moment we'll stop here with the results of laminar boundary layer, the Nusselt numbers for low Prandtl number, high Prandtl number, and Prandtl number of the order of 1. Okay, now come back to face to face, right? So in today's class we just did simple order of magnitude analysis of those equations and obtained forms of the solution, and then from experimental data or from complete analytical solution or numerical solution of the differential equation, one could fill in the constants that were to get, and accordingly got the expressions for Nusselt number. So we will be able to relate the fluid flow solution, heat transfer and mass transfer solutions for Prandtl number equal to 1 using the Reynolds analogy. In the next class I'll also introduce to you another analogy which can also help you to relate the fluid mechanics results to heat transfer and mass transfer results for non-unit Prandtl numbers as well. Okay, so with that then we will be able to complete the analogy, and even if one solution is given, the other solutions can be directly obtained from that. Okay, so we'll stop here and continue in the next lecture on the other concepts pertaining to the flat plate boundary layer. Okay, we'll stop here.